I hope it's okay.
Yes. Today's topic is Para-Ricci-like solitons with arbitrary potential or para-Sasaki-like Riemannian manifolds. Please go ahead.
Hello again to everyone. Firstly, some introductory words about the problem that I'm going to talk about. The concept of Ricci solitons was introduced by Hamilton in his work from 1982 as a special self-similar solution of Ricci flow equation. In other words, Ricci solitons represent a generalization of Einstein matrix on a Riemannian manifold, being generalized fixed points of the Ricci flow considered as a dynamical system. After that, a detailed study of Riemannian Ricci solitons can be found in the work number 9 here in my references from 2009. The study of Ricci solitons, just a second, sorry, began in 2008 by Sharma in his work. After that, the investigation of the geometric characteristics of the Ricci solitons hence continued on different types of almost contact metric manifolds. For example, you can see these works that I have put here. The notion after that, the generalization of this notion of Ricci soliton, the notion of eta Ricci soliton, is introduced by Cho and Kimura in 2009. Sorry, because this panel of the second. Yes, the investigation on eta Ricci solitons in the context of paracontact geometry were made by Dara Bwaga, for example, and Prakash and Mani. Recently, various geometers have extensively studied the properties of Ricci solitons in pseudo-Riemannian geometry and their generalizations. This interest is also based on the growing interest of this geometry of theoretical physicists and its relation into string theory. For further references of pseudo-Riemannian Ricci solitons, you could see these works that I have put it here. The object of our focus here in this work is the geometry of Riemannian manifolds with enormous paracontact structure corresponding to enormous paracomplex structure. This type of structure we call briefly here a pi structure, and these manifolds respectively Riemannian Π-manifolds. In these manifolds, the induced almost product structure on the paracontact distribution is traceless, and the restriction on the paracontact distribution of the almost paracontact structure is an almost paracomplex structure. In the work of Hristo Manev and Maria Stajkova from 2001, these manifolds are introduced and classified. Their investigation is continued after that from Hristo Manev and Tavkova. In the present paper, due to the presence of two associated metrics, we introduce and study our further generalization of the notion of a Ricci soliton and an eta Ricci soliton, namely we study para-Ricci-like solitons with arbitrary potential and para-Sasaki-like Riemannian Π-manifolds. Let me show some introductory words, preliminary words about the studied structures. By M phi psi eta G, we denote a Riemannian Π-manifold, where M is a differentiable odd-dimensional manifold, G is a Riemannian metric, and phi psi eta is an almost paracontact structure. Phi is tensor type 1, tensor field type 1, psi is a Riemann vector field, and eta is its dual 1 form, and identities 1 are satisfied. Consequently, the following properties are immediately derived from these basic identities, the properties 2. And as I said earlier, we have here associated metric G tilde of G on the manifold M, which is determined by equation number 3. G tilde is an indefinite metric of signature n plus 1 n, which is compatible with M, just like G. The Riemannian Π-manifolds are classified in the work of Manev and Stykova. This classification contains 11 basic classes denoted there by calligraphic F1 to 11, and it is made with respect to the fundamental tensor F defined in 4 and having the properties 5. The intersection of these basic classes is the class with condition f equal to 0. Also, we have the one forms associated with f, called Lie forms, which are defined in 6. Object of interest here in our work is the class of para-Sasaki-like spaces, which are defined in work number 16, our previous work with Stefan Ivanov and Hristo Manev. We obtained this set of Riemannian Π-manifolds from a specific cone construction, and these spaces are determined by the condition number 7. Let me remark that para-Sasaki-like Riemannian Π-manifolds form a subclass of the basic class F4 of the classification of the considered manifolds. In the same cited work, the truthfulness of the following basic identities for this class of manifolds are proved, number 8. And here we prove the truthfulness of proposition 1, which contains properties for the Ricci operator Q of arbitrary para-Sasaki-like Riemannian Π-manifold M phi excited G. Let me recall some definitions from our previous work with Hristo Manev. A manifold M is said to be para-Einstein-like with constants ABC if the Ricci tensor satisfies the following equality, and in the case when B vanishes or B and C vanishes, we call the manifold eta Einstein or well-known Einstein manifold. And if in the respective cases when A, B, and C are functions on M, we use the word almost before the definition. Also, let me recall a proposition for my previous work in symmetry about para-Sasaki-like Riemannian, arbitrary para-Sasaki-like Riemannian Π-manifold. If this manifold is almost para-Einstein-like with functions A, B, and C, then the scalar curvatures tau and tau tilde are constants, and tau tilde is equal to -2 times n, and the manifold is eta Einstein with the respective constants. Also, let me remark that tau and tau tilde stands for the scalar curvatures regarding the two associated metrics, respectively. Now, let me focus on Para-Ricci-like solitons. On these manifolds, in the previous work 17, the notion of Para-Ricci-like solitons with potential psi, the Riemann vector field psi, and constants lambda mu nu is introduced by 12. And as I explained before, it is a generalization of either Ricci soliton and Ricci soliton for mu equal to 0 and mu nu vanishes. We have these definitions, and here we have for functions lambda mu nu, the solitons are called in the respective cases with the word almost before. In the next work, work 18, we define the notion of Para-Ricci-like soliton with vertical potential, and we study it. This is the more general case when the potential is pointwise collinear with the real vector field xi. And now the aim of our work is to generalize this concept even more. When we can consider the potential to be arbitrary vector fields as follows. This notion of Para-Ricci-like soliton with arbitrary potential vector field V and constants lambda mu nu is defined by it is a Riemannian Π-manifold M admits this type of soliton if the Ricci tensor satisfies the equality 13, and we prove a theorem for these spaces. Let M be arbitrary para-Sasaki-like Riemannian Π-manifold, and it admits Para-Ricci-like soliton with arbitrary potential V and constants lambda mu nu. Then the identities for the constants number 14 are valid, and the covariant derivative of the vector field V with respect to psi is equal to phi V. Also, we proved the proposition 2.5 about the same structures if the manifold admits a Para-Ricci-like soliton with arbitrary vector with arbitrary potential V, then rho tau and tau till satisfies equality 15. And combining these two, this theorem and this proposition and the proposition 1.1 that I recalled earlier, we formulate the following theorem 2.6. Let M phi xi G be odd-dimensional para-Einstein, 2n plus 1 dimensional para-Einstein-like para-Sasaki-like Riemannian Π-manifold. If it admits a Para-Ricci-like soliton with arbitrary potential V, then the following identities are valid. Number 16. And after that, we prove assertions about the lowest dimension of the considered manifolds and their sectional curvatures. We have the definition of, we recall the definition of sectional curvature for an arbitrary non-degenerate two-plane by 17. And as I explained, in the lowest dimension of the considered manifolds, we distinguish two special types of two planes alpha with respect to the structure, respectively a phi homomorphic section and a psi section. And every phi homomorphic section has the basis of the form phi x phi squared x. And as I explained, we prove the following assertions. Let M phi xi G be a three-dimensional para-Sasaki-like Riemannian Π-manifold. If it admits a Para-Ricci-like soliton with arbitrary potential V, then the sectional curvature of its phi homomorphic sections are equal to 1, and the sectional curvature of its psi sections are equal to -1. And at the end of my presentation here now, I want to illustrate this theory with an appropriate example. Let M be a set of points in R3 with coordinates x1, x2, x3. We equip this set with the Riemannian Π structure, phi xi eta G, determined by 18. The triplet of vectors E1 to E3 determined in 19 forms an orthonormal phi basis of the tangent space. Therefore, we could calculate that 20. Then we have 20, and we could obtain easily the commutators of EI, put it here in number 21. The Lie algebra determined by these commutators 21 is proved in the work number 22 that the corresponding solvable Lie group of this Lie algebra equipped with Riemannian Π structure, phi theta G, is para-Sasaki-like Riemannian Π-manifold. Moreover, in this cited work, obtained the components of the Levitshev relation number R, rho Ig, as well as the values of the tau tilde, and the sectional curvature chi Ig. Here in the inequalities 22, 23 are given their values. And from the first equality of 23, we get the form of the Ricci tensor 24. So the manifold is a para-Einstein-like, para-Sasaki-like Riemannian Π-manifold with constants ABC equal to 0, 0, -2. And these results support theorem 2.6 and theorem 2.7 given here. And now let us consider vector field V determined as you can see here, 25 for arbitrary constant C1, C2, C3. By virtue of the respective equalities, we obtain equalities 26, and using them we could calculate the basic components of the Lie derivative of G with respect to V, and the non-zero ones are given here at the bottom of the list. And using them, the tensor LG has the following form given in 27. And we could deduce that the manifold M5 site G admits a Para-Ricci-like soliton with potential V determined in 25 and constants lambda, mu, and nu given here, which results are in accordance with the proved theorems in this work.
Professor Manev,
thank you for your attention.
Okay.
Thank you.
Thank you very much. Dear attendees, is there any question? Okay. Professor Manev, someone asked your presentation. Can you share your presentation?
Yeah. Yeah.
Email address or
my presentation.
In PDF file. Someone asked it.
In question, answer. Sorry.
Yeah.
Share PDF file with. How could I put it a PDF file in here, or I could email?
Okay.
But Makarakush, please put your email here, and I could send you my presentation.
Okay. Thank you, Professor.